Hello, I'm pleased to be here again for teaching this course in calculus at Unit 2, and this is our fourth lesson about classification of functions. In our last lesson, we spoke of the function, and we give a definition, a precise definition of function, and we said it's a correspondence rule between two elements. One belongs to a set, we call the domain, and the other one belongs to another set, which we call the range. And the operation itself maps every x into another y in a bigger codomain, and we show the codomain to be the set of real numbers, since we are dealing only with real functions. Now we have also to speak about the kind of function that we shall meet in our course. There are many of them, and we wish to classify them and put them into subdivisions in order to know what kind of functions we are facing in the future. In this lesson also, we shall be drawing some simple functions, because it's nice for the students to know how to draw simple functions, because it's shame that the students would always claim that should we, and this is a general question that the student always ask, should we draw the curve, Mr. So-and-so, or we just have to manipulate with algebra. So drawing really is not a big task. It's a simple thing. So we shall teach this. Now, in this lesson, we shall speak about the algebraic operations on functions, and then the classifications and the tests to know what kind of functions we have. And then we shall speak about various subdivisions of the way we write functions, like it's explicit, implicit, or parametric, etc. And then we list some geometric properties of functions, and again, at the end, we draw some simple ways of drawing graphs of functions. Now, first we start by the algebraic operations. Now, we can have, here are 4 rules of 4 different functions. For example, the one at the top here is the 9th root of x. And this is an algebraic function. Why is it algebraic? Because it uses algebraic manipulations. Here, we know that you use the calculator to calculate the values of functions. And calculators work with algebraic manipulations or algebraic operations. So this is the 9th root of x. Here, this is a rational function, x plus 3 over 2x plus 1. And while the first one, you have the domain of this function is r. Here you have the domain of this function is r, except the value minus half. And for the range of this function, we have to draw it, and you can exempt the value half, because if you take half, you get 2x plus 3 is equal to 2x plus 1, so 3 is not equal to 1, so to the range you have to exclude half. So this one is algebraic, and this one too, except that this one here, this is a root of x, and the root, as a matter of fact, is one of the numerical or algebraic operations. We have 5 algebraic operations, which is addition, subtraction, multiplication, division, and extraction of roots. So this is an extraction of root, and the extraction of roots are in fact rooted in history, because in the Greek were able to transform, for example, a rectangle using straight edge device instruments like ruler and compass, etc., into, for example, a square. And you deal with roots, like you have, for example, 2, and you have to rectangle of area 2, and you have to transform it into a square of side length square root of 2. So here you do a square root operation. So roots are one of the algebraic operations. And since all the numerical calculations are performed using algebraic operations, we call in this case this function algebraic function. So this is an algebraic function, and this one too, and this one here is an algebraic function, but here this one, although this one is rational, this one is irrational. In fact, this one is irrational, and this one too. This one here, the domain is this function. You have to make sure that x this under the root is positive, because you have square root. Have you had a cubic root, then there was no problem then, because the cubic root of a negative value is a negative value. This one here, is also an algebraic function because you deal with a square root and you have the cube of a parenthesis here, and then you have again a square root. So these four functions are in fact algebraic functions. Now this function here, which is the exponential function, it looks like 1 as a matter of fact because it's the addition, the sum of algebraic functions as well. You have 1, you have x squared. So these are algebraic functions. So the addition or the sum of algebraic functions is algebraic. But you have to watch out for something, is that when you say that algebraic functions are those for which the value of f is calculating using the 5 algebraic operations, you have to say also, you have to extend your definition by saying finite number of times. And here, the number of times by which you add these algebraic functions is infinite, and therefore e to the power x is not an algebraic function. Now, this is an algebraic function, p of x. It's called a polynomial. It's integral algebraic function, rational as well, where the coefficients can be real, but if the coefficients are real and transcendental like pi or e, this doesn't become therefore an algebraic function. Here you have an n integer, and this you encounter all the time. I mean, this is one of the most famous functions that you always have in calculus or in mathematics in general. The one at the bottom here, below, is also an algebraic function, is the form of a rational function. And this function here, the domain is R. The one at the top also is the domain of R. The man at the bottom here, the domain of R, except you have to exclude those roots of the denominator. So the domain of Q is R, except the root Ri. The root Ri meaning the root at which the denominator is equal to 0. This is a simple example in which you use the MATLAB. Here you have a polynomial, 5x cubed minus 3x squared minus 4x minus 1, and you wish to evaluate the value of the function at x is equal to 6. So you can use the MATLAB. The MATLAB I'll provide later if you are some files at which you can use the MATLAB, and it's very simple. It's only a batch files where you can just put just one sentence and you directly calculate the value of this function. And there are also other files or other subroutines in the MATLAB. MATLAB stands for mathematics, not mathematics library really, but matrix library, because when it was first designed in the early 80s, it is concerned, there was previous subroutines or previous packages, and from this they deduce this so-called very popular subroutine or very popular software in which you calculate all sorts of things concerning mathematics in general, not necessarily calculus. So here, for example, you have a rational function, and this rational function here, it has the denominators has roots at 3, minus 1, 2, and 1. So you say that this function here, it is defined for all values of x except the root of denominators, and you can calculate the roots again using your MATLAB subroutine. Now we have to come with the classification of functions. So the function, as numbers are classified into algebraic, like the rational and the square root of 2, etc., and transcendental functions, same thing with the function. The functions can either be algebraic or can be transcendental functions. Now the algebraic functions, they are rational or irrational, and we saw this before. The rational, like for example, x squared plus 1, and the irrational is the square root of x cubed minus 3, for example. These are irrational. Of course, the irrational functions, there are all sorts of functions, and they don't have a specific configuration. But you encounter all sorts of irrational shapes. Whereas the rational ones, they are easy. They can either be integral, like polynomials, like we saw before, or fractional, like rational ones. Whereas the irrational, they can take all sorts of configuration or shape. The transcendental functions, they are also of two kinds, either the elementary ones or the higher ones. Now, the higher ones, it's not common or it's not useful in our course because they pertain to functions that are used in in other more advanced applications, like, for example, mathematical physics and so forth, you encounter Riemann, zeta, Mathieu, gamma, beta, hypergeometric, all these kind of called advanced or higher transcendental functions, whereas in our course we shall be restricted to a class of elementary transcendental functions like the trigonometric one, like sine, cosine, cotan, tan, etc., and as well the inverse trigonometric functions as well, like the inverse of the sine function, cosine function. And we have also these two functions that we encounter a lot in economics, the logarithmic functions and the exponential functions. The trigonometric, as a matter of fact, is very old. The Hindu knew them, the Arab they excelled in the trigonometric identities. The ancient Egyptians also had them. They had the cotangent of an angle, which is the run divided by the rise. How many meters, for example, in fact, they measure in cubit or in 4 arms. How many 4 arms you have to run or walk for 1 cubit, for example, rise. Like, for example, the angle of inclination of pyramids, etc. So these are very old, whether trigonometric. The logarithmic and the exponential are rather new. The logarithm itself was known from the time of Napier in the 17th century, and the exponential function, e to the power x, etc., or 10 to the power x, it was a Swiss mathematician in the 18th century who studied them. So now we have all the kind of functions that we encounter. But usually there is a quick test. Instead of each time I'm giving you a function and you have to match it with this classification, there is a simple rule of doing that. The quick test is to check whether f is algebraic or not. Well, f is algebraic if it satisfies a simple algebraic equation of this sort, or polynomial of this sort, in which these functions R1 of x, R2 of x, etc., are rational functions of x. If your function satisfies y equal f of x, satisfied such an algebraic equation of this form in which the coefficients are rational function of x, then there you can say that your function is algebraic. For example, you have here an algebraic function. Why this is an algebraic? Because you can, if y is equal to this, then you can, for example, add y plus x, you get this to the left-hand side, y plus x squared becomes equal to x cubed plus 1. And then you expand this, you get this form here, and directly when you see this form here, in fact, this is an algebraic equation of the one that we just mentioned before. Why? Because you have your y squared, and then you have R1, this is R1, and then this is R2. So you have here y to the power n, because here you have n second degree, you have y squared plus R1y plus R2, and therefore, since these are rational functions of x, directly you can say that your original function is an algebraic function. Now, functions are seen in many ways, or in many shapes. They take different aspects or different configurations. For example, you have an explicit function. These are the most important as well, actually. When you have y is equal to f of x, you call this an explicit function because you say it explicitly. You say the value of y explicitly in terms of x. So you call this explicit functions. Whereas the implicit function when x and y are interrelated together. Whereas parametric, when, for example, you have another third parameter, for example, t, like in kinematics, where, for example, especially in other applications where you have x function of t and y is function of t. Now, for the first one, for example, this is called an explicit function. You see the x on the right-hand side and the y on the left-hand side only. Whereas your implicit function, when you see x and y are related together, for example, you have, for example, e to the xy is equal to 3. So e to the xy, you have x and y together. You don't isolate x from y. And actually, in sometimes when you isolate it, you can't do them. I mean, in simple situations, yes, you can transform an implicit function into an explicit one. But in most situations, you can't. It's difficult to solve x in terms of y or y in terms of x. And then you have a parametric form of function like this one here. So we take, for example, a simple example. So suppose, for example, you have y is equal to x squared. Here you have a Cartesian kind of representation of function. You have x, the x-axis, and you have y, and for each x there is a certain y, and this is an explicit function. And you wish to transform this, for example, into an explicit function or a parametric one. You can do this. How? Simply, you can write it this way. So you have f of x and y is equal to 0. So in fact, it looks silly, but it's not. It is a form of a function that you have x and y in one part, and f of x of y is equal to 0. But you can always substitute also, you can substitute x equal to t, in which case y is equal to t squared. So now you have here a parametric representation of the function. Not necessarily that you have y is equal to f of x, no. You have x given in terms of t and y also given in terms of t. So you can cancel t out of the two equations here to get y as a function of x. So now we transformed a Cartesian function explicit in the form of explicit function into an explicit and into a parametric function. For example, here this is a Cartesian kind of implicit function because you have f of x and y equal to 0. Now this represents what? This represents a circle. How? Because you can directly, you have here x minus 1 square plus y square is equal to 4. So directly you can have your, here you have your center 1 and 0, and this is x and this is y, and here you have the diameter the radius is equal to 2. So directly you have a function circle like this. This run here to 3, and this becomes equal to minus 1, so that you have here 2 and 2 and 2. So the center as 1 and 0, and it directly says here this is a circle of radius 1, of radius 2, and of center 1 and 0. So, so this function here, as you see, can be transformed, or from which you can extract two functions. Why? Because for each value of x, you see that there are two values of y, and you can see it directly here on the graph. Here you have for each x, for example, for x is equal to 1, y is equal to what? Minus 2 or plus 2. So for each x there is two y's, and this can't be so. This is rejected. It's impossible, because we said before that the function maps one x into a unique y. But since one x gives two y, then this is not a function. It's a kind of relation which relates x to y. And therefore we can extract from this two functions. One is square root of 4 minus x minus 1, and this is a function, and the other one also is. So you get two functions out of one. And on your graph here, you can have the upper part represents a function, and the lower part, it represents another function. Why? Because you want for each x there is one y, so you have two functions. As for the domain of this function, from the graph directly you see that the domain lies from minus 1 to 3. How you get this directly here? We said before, in order to obtain the domain of the function, what is inside the square root must be positive. So you set x minus 1 squared less than 4, or the modulus of x minus 1 less than 2. It means that x lies between minus 1 and 3. So these two functions have the same domain. Now this function here can be transformed into, as I said, two functions. One is the square root of 4 minus x minus 1 square, and the other one is minus square root of 4 minus x minus 1 square. Both work from minus 1 to 3, and both have center 1 and 0. So these two functions are Cartesian, they are explicit because y given in terms of x. But you can also transform, for example, let's take the first one. The first one, which is x minus 1, which is given y is equal to the square root of 4 minus x minus 1 square. You can transform into a parametric form. How? You can just take, for example, x is equal to 1 plus 2 cosine t. If you take x is equal to 1 plus 2 cosine t and you substitute the value of y, because here you have y is equal to what? You have y is equal to the square root of 4 minus x minus 1 square. So if you take this equal to 1 plus 2 cosine t, which is x, so 1 cancels with 1. You have here 4. This becomes equal to 4 cosine square t. So you have the square root of 4 minus 4, you get 2 outside, and so you get 1 minus cosine square, which is sine square. Under square root, you get what? Y is equal to 2 sine t. So you have here y is equal to 2 sine t. So here t lies from what? Lies, since t represents an angle, because you see directly that x, where is x? This is all the value of x. Here, the value of x is equal to 1, which is this part, plus here the projection of this radius. The projection of this radius is equal to what? Is equal to 2, which is the radius, times cosine of this angle. And you get the whole of x. As to y, this is the value of y. The value of y is equal to what? Is equal to 2 times the sine of this angle, and you get y. So here t lies from t to, from 0 to pi. Now, suppose first we would like to, for example, take the same equation. For example, you have y is equal to minus square root. We take the one below, which is the second one. This is another function, as we said, like this. And here you have 1 and 0, starting from minus 1 till 3. And we wish to transform this into a parametric function. So what we do, we can do the same thing. We can take x is equal to 1 plus 2 cosine t, and 1 is equal to 2y sine t. But t, in which case, lies starting from this value, which is here, pi till 2 pi. In other words, t in which case will lie in the interval from pi till 2 pi. Because we start from here, turn till the point from minus 1 to 3. If we wish to treat it like the one before, what you can do, you can take t is equal to pi plus u. So when t is equal to pi, u becomes equal to 0. And when t is equal to 2 pi, u is equal to pi. And in which case, you can treat now this piece here, this angle here is equal to u. So now, instead of saying that t starts from t till 2 pi, from pi, here is t, this is this big angle. From pi till 2 pi, you can say, no, u start from 0 till pi. And in which case, if you substitute t in these two equations, what you get? You get x is equal to what? You get x is equal to 1 cosine plus 2 cosine pi plus u, which is equal to what? Is equal to minus cosine u, whereas y is equal to 2 sine pi plus u, which is equal to minus 2 sine u. So you have now a new coordinates, x and y, such that the parameter t starts from 0 till pi, subject to x is equal to 1 minus 2 cosine u, and y is equal to minus 2 sine u. And in fact, the sine function is positive from 0 to pi, but here y is negative because it's below the x-axis. So this is one way of doing it. Now this is called a cycloid. Again, this is a parametric equation. Well, the one before, the equation we dealt with before was a kind of implicit equation. We want to transform it into a parametric equation. Now this one here is the opposite. This is a parametric equation, and we want to transform it into an explicit or an implicit equation, a Cartesian implicit equation. I mean, we transform from parametric into implicit. Now, this is called cycloid. A cycloid is a locus of a fixed point. You have a circle, and this circle slides, and in fact, it slides on a rough surface. In other words, it rotates, because if it slides, then it's different. It rotates such that without sliding. It rotates like this from this point till this point. So t here represents the angle subtended with the vertical axis, and t runs from 0 to 2 pi. So you get y here is 0 and y is 0. And at t is equal to pi by 2, you get here y is equal to when t is equal to pi, you have here minus 1, so you get 2a, y is equal to a, whereas when t is equal to pi, y becomes 0, and x runs from 0 to 2 pi a. And here, this cycloid is very famous curve. Why? Because it was the third curve in history to have been the length of which has been calculated. The first circle, the first curve in history to have been calculated, the length is the circle. The second is the logarithmic spiral, and this is the third one. And it's nice to see it done. Here is the circle, and the circle rotates such that it runs on this straight line. So if you draw a curve like this, here is your cycloid. It's the locus of the point which is fixed. The point is fixed whether the circle rotates. So you get this. Of course, you can choose a point outside the circle, like this one, for example, and you draw the curve. You get sometimes it says hypocycloid, undercycloid. So these are called. This is called a cycloid. This is applet has been devised at Cairo University in the Faculty of Engineering in order to exemplify the concepts of locus and parametric equations, how they function. So we come back here now to this. Now, if suppose we wish to transform our Cartesian, this is a parametric equation, and we wish to transform this into a Cartesian equation, but in the form of implicit. In other words, we want to cancel t out of the two equations to get a relation between y and x. So it's not all the time easy. It's not all the time easy whether you transform from any sort of function, explicit, whether implicit or explicit, into, for example, transforming from implicit to explicit function is not easy. A configuration or a shape or type, it's not always easy. But sometimes it is. For example, to see this, we want to witness here how complicated is the way or the steps in which we seek to transform this equation into an implicit one. First of all, we expand this. You have y minus a is equal to minus a cosine t. Then we square both sides. Then we expand y minus a square to obtain y plus a square minus 2ay is equal to a square plus cosine square t. And then what we do is that we get a square minus a square cosine square t on the right hand side, and the remain 2ay minus y square. But 1 minus cosine square t is equal to sine square t. So again here you have this, the 2ay minus y square is equal to a square sine square t. Of course, you may lose the steps because I myself find difficulty in obtaining this or in finding the way how should I follow, what kind of steps should I follow until I end up with an implicit equation. So it's not all the time easy. And then what I did is that I obtained a sine t. But then I can from here calculate x, because I have x is equal to a times t minus sine t. Now I have a times sine t here. So I can now calculate t. From here, since sine t is equal to the square root of this, so at the end I can calculate the value of t, which is equal to x plus the square root of ay minus y squared divided by a, and from there on I can get y then, because y is equal to a times 1 minus cosine t. So at the end I obtain something like this, and this is actually is not easy. This is an implicit equation gathering x by to y, and I cancel t between the two equations. So you see now it's not easy to all the time to cancel out a parameter between two parametric equations. Now we have also some geometric properties, of functions. Functions, for example, they can be positive, they can be increasing, they can be decreasing. They have all sorts of geometric properties, not only explicit, implicit, etc. They have geometric properties, meaning that the type of configuration or the shape they take on when you represent them as graph on the xy axis. For example, this one here, y is equal to x to the power 2 over 3. This is it's called the third root of x squared, and this is an even function. An even function here, how did you know that it's even function? The meaning of even function is that it is symmetric about the y-axis. In other words, when you draw it for x positive, the value of y is equal that for x negative. So this is called an even function, and you check this by writing f of minus x is equal to fx. In other words, when you substitute x here by minus x, you get the same value of y. So for example, this function here, they tell you check the parity of this function. All you have to do is that you replace x by minus x. If you replace x by minus x, what you get? You get the same thing. You get here x squared, and the modulus of minus x is modulus of x. So you get the same function before, the same explicit function before, which means that f of minus x is equal to f of x. So this function is even. Whereas, for example, if you have a function like this is the third root of x. This function is symmetric about the origin. In other words, when you put x, for example, is equal to 27, you get 3. When you put x is equal to minus 27, you get minus 3. So it's symmetric about the origin. In other words, f of minus x is equal to minus f of x. What you do is, all you have to do is to substitute here, you replace x by minus x to obtain minus x to the power third is equal to minus x to the power third. This is called an odd function. In fact, sometimes you have complicated or cumbersome functions. You can split them away. In other words, suppose you have an even function multiplied by an odd function. Then the product of an even function times an odd function is an odd function. An even function times an even function is even. And an odd function times an odd function is even. So you don't have to, you can split them away. For example, you have, x times sine x. X is odd and sine x is odd. So x sine x becomes even. This simplifies the way you check the parity of x. So, for example, this one, f1 of x, f of minus x, you divide f of minus x here, 1 over minus x. You substitute here x by minus x, so you get minus 1 over x. This is minus f of x. And you directly watch out here that the value of y here is positive, and for x, for example, is equal to 2, and it's equal to minus the value on the other side when x is equal to minus 2. So we say that there is a symmetry around the origin. Again, this is it's called a monotonically increased function. It's increased all the time. And this is the rule for it. If you find that f of x2 is always greater than f of x1, when x2 greater than x1, you say this is a monotonically increased function. This is a periodic function. Periodic function exists in nature. For example, your electric cardiogram, when you check your heart, your systolic and diastolic, you find that there are beats, and they usually duplicate themselves. So it's called a periodic function. With here, the period is tau. In other words, every tau, the function doubles or repeats itself. Like the moon itself, it becomes a full moon, then a crescent, then a full moon again. So this is a periodic function of the moon. Not all function must be even, odd, or neither. No, you can have a function like this one. This one is neither monotonic increasing, neither decreasing, nor periodic, nor even, nor odd. So it's not necessarily, and this is a very simple function. So most of the functions, in fact, they don't adhere to these rules or geometric properties that we have just listed. No, in general, a function may not be having any of these choices of parity or other geometric properties. Now, to draw simple graphs of functions, this is important because the student, in fact, they have to know how to draw graphs. Now, this is a simple graph. Y is equal to x squared. This is a parabola, and we saw before. Now, suppose you add up 3, for example. How do you draw x squared plus 3? All you have to do is to elevate your curve. Here, the curve would be elevated by 3 units. So x squared plus 3 would be parallel to x squared, except that it's elevated, added up with the value of 3. Whereas if you subtract from x squared minus 3, it means that you lower down your curve by minus 3. You can always shift your curve to the right or to the left. For example, this one here is y is equal to x squared. If you want to draw x minus 3 squared, it's easy. All you have to do is that you can shift your y-axis to the left, or you can shift your curve to the right by 3. In other words, here is your curve. You shift it till this curve here. This curve, instead of having a minimum at the point x equals 0, it will have its minimum at the point x equal to 3. And on the other side, when you add up x plus 3 squared, it means that you shift your curve to the left. So any equation y is equal to f of x plus d, it means that you shift it to the left, and y is equal to f of x minus d, you shift it to the right. So you have here the new equation from the old equation. All you have to do is that you can shift it upwards, downwards, a distance c, by adding up either to y or to x. If you add up to x, then you shift to the left. If you add up to y, you shift it upper, and contrary, if you subtract, then you shift them below. For example, the function here, you want to draw the graph of y is equal to minus modulus x plus 1. This is a rule that you always have to memorize. You always start with the easiest graph. What is the easiest graph here? Is modulus x. You know modulus x, we know very well modulus x. And it's like this, but inverted above. And we saw it before, like this, which has x here and minus x there. So this is minus x. You start by minus modulus x. After you start by minus modulus x, you shift it to the left by 1 to obtain this one. This becomes what? Minus modulus x plus 1. And then you shift it above. by 2 units to become 2 minus modulus x plus 1. And this is the way you do it. You always start by the easiest way of doing it, by the one that it is the easiest of them. For example, this is, you want to draw the curve. Y is equal to minus 3 plus the square root of 3 minus 2x minus x squared. Now, this looks a little bit complicated, but this is not so, as a matter of fact. How? First of all, when you see a polynomial under the square root, you wish to do something called completing the square. What's the meaning of completing the square? In other words, you get x squared and x in one bracket and the remaining outside. Here, for example, suppose you want to expand this. What is the value of x plus 1 squared? It's x squared plus 1 plus 2x. So you get minus x squared and minus 2x. Here are they. But then you have here minus 1. So what should you add up to obtain 3? You add up 4. So when you expand 4 minus x plus 1 squared, in fact, you obtain 3 minus 2x minus x squared. And this you can do on any quadratic function, irrespective of the coefficients. You can always complete the square. Now, this looks familiar. Why? Because we've seen the equation of the circle. There is here minus 3. So it means that the center becomes shifted at the point plus minus 3. And then here you have 4, instead of 4 minus x squared, you have 4 minus x plus 1 squared. So which is the easiest of the functions you should start with? In my view, you start with y is equal to 4 minus x squared. What is that? That's the equation of a circle, of center at the point 0 and 0, and of radius equal to what? Equal to 2. Because when you square this, you got x squared plus y squared is equal to 4. This is equation of a circle, center at the origin and of radius 2. You start from this. And after you start from this, what you do here, you move from this to till the square root of what? Of 4 minus x plus 1 squared. Forget about minus 3. It means that you have to shift it to the left. And then onwards, you add up minus 3. In other words, you lower down. So the way you do it, here it is. You start by the easiest. This is the easiest, which is the circle, the graph of the circle, which is of center at the origin and of radius 2. And then you move it to the left. When you move it to the left, you get the square root of 4 minus x plus 1 squared. And we said before, f of x plus d, you move to the left by minus d. So here, x, if you want the square root of 4 minus x minus 1 all to the square, then you should have transformed it or shifted or move it to the right. But since you add a plus, then you must shift the y-axis to the right by 1, or you shift your graph to the left by minus 1. So here, what you do here, the new center would be the point minus 1 here. It will be the point minus 1 and 0. So you got your new graph. So your new graph here, again, it's a semicircle, exactly like this one, except that with the same radius as well, which is 2, except that the center is shifted from the origin to the point minus 1 and 0. And then if you want to reach the final result, the graph that you wish to draw, you add up minus 3. The meaning of adding minus 3, in other words, that you lower down your graph by minus 3. In other words, the point, your center will be, instead of the point minus 1 and 0, it will be minus 1 and minus 3, etc. So you do them in 3 steps. You start by the easiest, and then you move towards the difficult one. So now we come up to the end of this lesson. In this lesson, to summarize, we spoke about the classification of functions, because later on we shall speak about a special kind of functions, the one that we are interested in, and we saw what is the test in order to differentiate whether a function is algebraic or not, and we spoke about the important kind of functions, rational, irrational, and transcendental. And then we said that there is a way of representing the function, whether it could be explicit, it could be implicit, and it could be parametric as well. And there are other, as a matter of fact, forms like polar representation, but these are the most important. And you can shift from one type to the other one. Sometimes you can do it easily, sometimes not. But these are all the functions that you need to know, and that the function that we shall explore in greater detail. So until we meet again, I'm wishing you good luck, and thank you for your attention.